Okay, our next speaker is Dr. Dhiraj Hazra. He will be talking about generating primordial black holes and secondary gravitational waves in two-field models of inflation. Dhiraj, you will have 25 minutes and then 5 minutes for questions. I will warn you after 20 minutes. You
Sure,
can start now.
you can see my slides in this full screen mode, and
yeah, absolutely.
you can see my pointer as well moving.
Absolutely.
Okay, great. Thanks, Ram.
Yes,
and
yes.
Thanks a lot for the organizers for inviting me in this beautiful school and workshop. Okay, so we have been listening to primordial black holes, generation of primordial black holes, and the constraints from the morning. And Rajiv has also given you the overview of generating primordial black holes from the single field inflection point model of inflation. So what I'm going to talk about is generation of the same things, the primordial black holes and the small scale gravitational waves, but in the two field models of inflation. I'm going to motivate why we need the two field models of inflation and what are the differences. And even in the two field models of inflation, there are classifications. So and I will not spend much time on the press-sector formalism and the generation of the primordial black hole, the formula, etc., because Rajiv has already discussed those things in his talk. So let me first start with by discussing what we know till now. We know that the primordial black holes can contribute to the energy density of the cold dark matters, and it is known that it can, in certain windows, it can contribute to the fullest. That means that total mass of the or total density of the cold dark matter can be completely contributed by the primordial black holes. First of all, let me just tell you that this primordial black holes, the concept and the interest that people are working with is it has spark after the detection of the gravitational waves, but it is not that it has originated from there, because there has been seminal works by Professor Bernard Kerr and Professor Juan Garcia Bellido before, much before even the LIGO detected the gravitational waves. So there were works before the detection, but the interest has been renewed after the detection. And over time, as Rajiv showed, that the constraints on the primordial black holes, the fraction of the primordial black holes as the cold dark matter, has become tighter and tighter over time, and we have only left with two windows where we can say that, okay, the primordial black holes can contribute to the cold dark matter to the fullest. And these are the two windows are around 10⁻⁻16 solar mass and 10⁻⁻12 solar masses. So these, if the primordial black holes are of the have the mass of the order of 10⁻⁻16 to 10⁻⁻12, then they can contribute to the CDM density to the fullest. Otherwise, they can contribute to the 10% or 20% or so. And also these densities has a correlation with the stochastic background gravitational waves. So we can have another constraints from that part as well. And there are lots of mechanisms, and I'll be talking about only inflation that provides this mechanism to generate this large bump in the spectrum of curvature perturbation. So there are many ways to do that. You can have sharp sharp potential where you can have a fast roll. So inflation usually gives you a slow roll, and that gives you a nearly scale invariant power spectrum in the CMB, which we are able to constrain pretty accurately. But if you have a large bump, in order to generate that large bump, you need to have departure from slow roll. In order to do that, either you will have a sharpness in the potential where the scalar field rolls down fast, or you have this ultra slow roll that Rajiv explained. So what happens is that your Hubble flow function, or the epsilon, or the higher derivatives of epsilon, sees a peak, and the modes that leaves the Hubble radius around those E folds where the epsilon has the peak feels the effect and leads to amplification in the curvature perturbation, and that reflects in the primordial power spectrum. And when those scales re-enter the horizon in the radiation dominated or matter dominated era, they collapse and form structures, and that's how this mechanism works. And also, it is not just the primordial black holes as a structure formation that basically comes as a resultant effect of the inflation with a sharp potential or the fast roll, but also it can generate gravitational waves by the second order effects. Okay. So just let me review a few inflationary models or the free inflationary frameworks that can that gives rise to this kind of scenarios where primordial black holes are generated. First of all, there are single field local peak scenarios where you have a break in the inflation potential, and the people have worked on these scenarios in these papers. There are inflection point scenarios. Rajiv just explained his work in this paper. And there are other works as well by Ivan Garcia Bellido and Germani and a few others. Non-trivial sound speed. So if you have canonical slow roll inflation or canonical inflationary Lagrangian, the speed of sound is equal to 1. But if you have non-canonical effects, non-canonical terms in the Lagrangian, it can give rise to non-trivial sound speed. That also can give rise to peaks in the primordial power spectrum. If you go to multiple models, there can be hybrid inflation. Such scenarios are explored by Ivan Garcia Bellido, Kawaguchi, and Sebastian Kresse. What happens is that you have two field models, phi and chi, let's say, and you have a potential. You have a potential, which is a function of this phi chi, and they have they are coupled. The potential is coupled. In those cases, also you can see there are turn in the field spaces, and they give rise to larger bumps in the primordial power spectrum with respect to the scale invariant spectrum. So why we go to multi-field models in our paper? So this is because of few reasons. One is that two-field model can provide the general description of effective single-field model. For example, if you take a single-field model, in order to get the primordial power spectrum with a bump, you need to reverse engineer and get some potential that can lead to sharpness in the potential, and that in result gives you fast roll. For that, you need to introduce certain break in the potential or certain inflection point or certain ad hoc terms like tan hyperbolic or Gaussian terms in the potential, and that leads to the peaks. However, in the multi-field model, you can work with simpler potentials, and a turn in the field trajectory leads to the amplification. If you have a turn in the field trajectory, it actually boosts up the epsilon or the Hubble flow functions, epsilon and its derivative. So you get amplification in the primordial power spectrum. And it also allows you to have a two-stage inflation, where the first stage of inflation is ruled by the first field, and the second stage of inflation is ruled by the second field. After the first field comes down to the bottom of the potential, oscillates, and gets frozen. So you have two-stage inflation, and it also provides richer dynamics in a single framework. So if you have a two-field model, you have a richer dynamics. You can explore this richer dynamics in one framework. You do not have to change your parameters much or your potential much. The drawbacks are these are difficult to solve because it is not just a single curvature perturbation or Mukhanov-Sasaki equation. There are coupled iso-curvature perturbations, and there are different initial conditions as well. Secondly, it has more parameters. Two-field models have more parameters because the potential needs to, it has a potential with respect to the two fields, and also it has initial conditions that are, for example, if there are phi and chi, there are two fields, you have an initial, where the start, the initial field value, they are also free parameters. And also it can give rise to large non-Gaussianities, which I will not discuss in this lecture. So large non-Gaussianities can also be something that can come from two-field model of inflation, which may be ruled out if the large non-Gaussianities come in the Planck regime. Although the regime we are interested in, it is much smaller than the Planck probe scales. Okay, so I'll be talking about the work that I did with Matteo, Fabio, George, Sriram, and Alexei. This work assumes the following action, which is the gravity is simple Einsteinian gravity given by this Ricci scalar, and these are the kinetic terms in the Lagrangian. So phi square, del phi square, and del chi square. This is the non-canonical coupling in the kinetic term, and there's a potential given by V phi of phi and chi. What we are taking here is the potential is not coupled in the fields, so the potential can be written as V phi plus V chi. However, the coupling is in the is in the non-canonical nature, and if the coupling is in the kinetic sector. So as you can see, the kinetic term of the chi field is modified by this f of phi. And the f of phi, we are using this form exponential of twice b of phi. I'll be talking about two scenarios. One is where the b of phi is linear in phi, and another is when it is non-linear of phi square. And if you solve this Klein-Gordon equation, if you have minimized this action, you will get this Klein-Gordon equation given by this. And as you can see, if it is b of phi is linear, then the Klein-Gordon equation for the two fields can be written as these two equations. What you do is that you solve these equations, and you get the background evolution. We are not going to the perturbation right now. So in this plot, I am just plotting the background evolution. So as a toy model, we are using this KKLTI form of phi potential, okay? So which is given as this, and for the chi potential, we are taking a standard quadratic potential, 1 chi square and chi square. And the Hubble parameter is written in terms of this, that it is phi dot square plus chi dot square. See the non-canonical term enters here. And these are the Friedmann equations that you can write using the stress energy tensor that you can obtain from here, okay? Now, these are the evolutions. And as you can see that these are the phi fields, these are the phi and chi fields. Given this potential, we start from a value of 7 here. And we can see that the first field phi rolls down to the bottom of the potential, it oscillates, and then it stays frozen, while the chi field stays frozen all the time while the phi field was evolving. So it doesn't take part in the inflation whatsoever till the time phi comes down. After that, the second field takes over, and you have the second stage of inflation. The first stage of inflation is given by this, and the second stage of inflation is given by the other term. The non-canonical coupling is given in this color bar. As you can see that you have differences in the field evolution. However, it is not very evident in the field evolution. Neither it is evident in the slow roll parameters. For example, the first slow roll parameter is given by minus hn by 8. So it is logarithmic derivative of the Hubble parameter with respect to the E folds, all right? So you can see that it is, we have different endpoints of inflation where epsilon becomes 1 finally after this sharp departure from slow roll. So here the inflaton is, both the inflaton are slowly rolling, and there is a peak, and then after that it comes down, and then finally it goes to 1. And the second slow roll parameter is the eta, is the parameter eta, and just a second, I'm sorry. I'm sorry, my daughter certainly came in. Okay. So the second slow roll parameter is given by this parameter eta, and you can see that here also it actually departs from the slow roll. And one important point is to note here is the effective mass of the isocurvature perturbations. So if you have inflation with two scalar fields, you can have curvature and as well as the isocurvature perturbation. So the effective mass of the isocurvature perturbation is given by this. And you can see that while the background evolution was not, you cannot see much difference in the background evolution given by this B1, which is the non-canonical coupling. The isocurvature mass, you can see the change in this zoomed plot here. So isocurvature mass goes negative, and you have a temporary tachyonic instability, which sources this curvature perturbation. I'm going to describe it later. So as I explained, the heavier field phi drives the first phase, and the lighter field chi drives the second phase. And phi oscillates at the minima, and therefore the intermediate fast roll takes place. Then let's go back to the perturbation. The metric perturbation is given as this. You can perturb your metric. Your standard Friedmann-Robertson-Walker metric is given by dt square and square t dx square, and then you perturb the metric with this phi terms, capital phi terms. With that, you can write the Mukhanov-Sasaki equations with the change of variables. For example, you write a sigma term and the S term, which actually relates to the curvature and isocurvature perturbations. So, and these are the Mukhanov-Sasaki variables. And as you can see, with respect to compared to the single field inflation model, you have lots of other terms, and mainly the other terms are the coupling terms. For example, Q sigma couples to the delta S with these terms. For example, the delta S comes here, and also the delta is coupled to Q sigma, as you can see here. So there are feedback effects, all right? We can make another change of variables is that the R and S, which are curvature and isocurvature perturbations, and the equations look much simpler in this change of variables. And you can see that in this single field inflation, it is just R double dot plus this term, R dot plus K square by S square R equal to 0. But in this, what happens in this two field case is that you have this coupling term as well as you have this isocurvature term, all right? So which actually isocurvature gets generated, and it also sources the curvature perturbations. Now, there is some important point I'd like to mention is that it is not just that what you do in the standard case is that you start from a point where you impose the bunch division initial condition. If in a single field inflation, impose the bunch division initial condition when the modes are sufficiently inside the Hubble radius, where the modes behave like a free wave. And then from there, you evolve them. And at certain point in the super Hubble scale, where K by AH is very, very less than 1, they freezes. And we evaluate the primordial power spectrum at the super Hubble scale. However, this is not true in the two-field case. In two-field case, as I said, you have isocurvature perturbation, so you can have the bunch division initial condition also for the isocurvature perturbations. But if you examine the equations properly, you will see that the isocurvature perturbation and the curvature perturbation are decoupled at the sub-Hubble scale. So you need to impose the initial condition in such a way that they stay decoupled, but the coupling happens afterwards. So in order to do that, you start with two sets of initial condition. In the first set of initial condition at the sub-Hubble scale, you say that your curvature perturbation follows the bunch division initial condition, while the isocurvature is 0. So they are decoupled. And in the second case, you say that your curvature perturbation is 0, while your isocurvature perturbation follows the bunch division initial condition. All right. And the resultant power spectrum, primordial power spectrum, is the sum of these two. So you start with two sets of initial condition, you get two power spectra, and then you add those power spectra. You also get the primordial isocurvature power spectra in the same way, and the correlation is given by this. The isocurvature source curvature perturbation is this one, where you have assumed that your initial curvature perturbation was 0, but isocurvature perturbation was following bunch division initial condition. So it is completely sourced by isocurvature perturbations.
Dhiraj, you have about 5 minutes.
Okay, I'm sorry. I am sorry. I was pretty slow in the initial part. So what happens is that the modes leave the Hubble radius at certain scales and they re-enter. So the smallest mode that leaves the Hubble radius and re-enter the horizon are the modes responsible for the generation of the primordial black holes. So we use the code bingo. We basically modify the code bingo for the two-field models with non-canonical Lagrangians, and we solve the background and curvature perturbation equations without any analytical approximations. And what we find as the simple quantities such as NS and R are given as this for different observations. For example, what I listing here in the left panel is the different upcoming observation, SK, LISA, BBO, and Einstein telescope. And they peak at certain scales, a certain wave number. And we want to generate the stochastic background gravitational wave at those wave numbers and primordial black holes corresponding to those mass scales. And if you want to generate in our those peaks in the primordial power spectrum at those scales, the NS and R we get from our model are this. As you can see that the NS here are very much consistent with the Planck. However, the NS here is not consistent. However, as I said, it is a toy model. You can change the potential and get, if there is a peak, you can change the potential and get the desired NS. So what happens here is that the isocurvature sourcing of the curvature perturbation that I was mentioning before. So here you can see that these are the four quantities R1, R2, S1, and S2, which gives rise to the final curvature and isocurvature perturbation. So, and I have plotted in black is the epsilon. This is the part, the red band is the part where the isocurvature mass goes negative. The effective isocurvature mass goes negative. So, for example, I'm trying to get a peak in the primordial power spectrum at around 10 power 12 megaparsec inverse. So, if I evolve the modes, we see that the isocurvature sourcing happens around this region, but the modes that are before the modes, the k values that are lower than this 10 power minus 12 do not see this amplification. The amplification decays, it amplifies and then they get decays, and the modes that are afterwards, they gets amplified afterwards, but do not see the amplification in the resultant primordial power spectrum. However, here you can see that R1, this is the curvature perturbation, and this is the isocurvature source curvature perturbation. You can see that this is the isocurvature perturbation, the feedback effect. The yellow curve actually pushes the green one here, and that gives rise to a bump in the primordial power spectrum. The bump corresponds to these bumps in the primordial power spectrum. This one is the cosmic microwave background regime, and after that these are the small scales like white dwarfs and all that. And then these are the observational range of SK, ELISA, BBO, and Einstein telescope. We plot it for the 25 decades, and we plot it for different values of the non-canonical coupling term. Okay. PBH formation, we use press sector, as Rajiv said. We are using the spherical collapse, and I'm not going to the formulation anymore here. The scaling relation between K and the mass of the primordial black holes are given as this. So K at 10 power 6 megaparsec inverse corresponds to 35 solar mass black holes, and K of 10 power minus 10 power 15 megaparsec inverse, very small scale, corresponds to the black holes of the order of 10 power minus 20 solar masses, 19 to 20 solar masses, which have been already evaporated. And these are the observational constraints that you can find, and we are not showing all of them, but these are the observational window where you can get constraints. You do not have constraints actually, and you can get your primordial black holes to contribute to the full mass of the full density of the cold dark matters. So you can see that the total fraction of primordial black holes to the cold dark matter is 1 in these cases, in these scales. However, at the SK scale, it is of the order of 0.01. So it only contributes to 1%. So it is actually the integration of the FPBH along the solar mass, along the mass of the black holes. Again, the gravitational waves, primordial gravitational waves. So these are actually the stochastic background gravitational waves that are sourced by as a second order by the large scalar over densities. And here the second order terms come here, PR and PR, as you can see. And this is the two integral that you need to solve. We solve this completely numerically, and we find that they actually have large signatures of gravitational waves, which falls under the threshold of the upcoming observations. So one good thing is that even if the primordial black holes do not contribute to the energy density of the cold dark matter to the fullest, they will have strong signals in the relic density of the stochastic background gravitational waves. So you can have two-way constraints. If we are not able to find the primordial black holes to contribute to the cold dark matter, we will be able to detect it from the gravitational wave observations. Okay, so I would say that SBDGWs are better tracer than the cold dark matter candidates. Okay, what happens if we change the coupling? If we change the nature of the coupling, we are using a coupling of linear order. The B of phi is B1 times phi, and now we are changing to second order. We are assuming that FB is twice exponential of twice B2 phi square. And it actually, what happens is that it broadens the peak. It broadens the peak of the isocurvature mass. It broadens the peak of the primordial power spectrum. And therefore, it broadens the peak of the FPBH as well, the PBH fraction. And also here you get the broadening of the peak. So this is the effect of the nonlinear coupling if you change the coupling. If you change the ratio of the potential Okay, so if you change the ratio of the potential V0, which is the potential for the phi field, and m chi, which is the mass of the second field, if we denote it as R and we test different values of R, as you can see that we are using 30, 500 and up to 3000 values of R, and we plot the quantities. What happens is that you find violent oscillations in the epsilon, in the Hubble flow functions, and they evolve, and then finally ends the inflation. You have multi-peak structure. Okay, so you have multi-peak structure in these cases in the primordial pulse spectrum. These multi-peaks leads to multi-peak structure in the fraction of the primordial black hole. So it no longer is monochromatic. You have two-peak structure, and here all of the cases we have, we have restricted to the cases where the fraction of the PBH is 1. So it actually completely describes the whole dark matter density. You also have multi-peak structure here in the background gravitational waves, but it will be very hard to detect this.
Wind up.
Yes, I'm in the summary slide. I'm going to the summary slide next. So you can see that there are multi-peak structure, but it will be very hard to detect them. First, we have to detect the first peak, and then we can talk about the features in that peak. Okay, so to summarize, two-stage inflation driven by two fields with large non-canonical coupling gives large amplification to the primordial pulse spectrum. Maximal growth rate can occur with ns equal to 4, which is consistent with Chris-Bynes results. And beyond the threshold, large perturbations collapse into PBHs and re-enter when they re-enter to the Hubble radius during the radiation-dominated epoch before the Big Bang nucleosynthesis. And it also gives the relic density, give rise to the peak in the relic density of gravitational waves. And though we have used a toy model of the potential here, the mechanism is pretty generic. You can use any potential, but if you use the non-canonical coupling, you will get this kind of amplification. And we have already discussed this non-canonical changing of the non-canonical coupling gives rise to enhancement and widening of the peak. And we can have, constrain these models jointly. We have not considered the effect of non-Gaussianities, but there can be strong effect of non-Gaussianities, as has been discussed in these papers. With that, I would like to stop. Thank you very much. If you have
thank you, Dhiraj. I don't see any questions or comments. Maybe I will request the audience to either come forward and ask the questions, or the only thing Suratna had asked was whether how important is the choice of the form of the potential in this two-field model.
I think
maybe we can take that question.
Yes, I think it is pretty generic. You can choose any potential. For example, we have chosen this potential because it gives, in most of the cases, am I still screen sharing?
Yes.
Okay, so you can see this slide. So we have taken this potential because in most of the cases of LISA, BBO, and the Einstein telescope, you get reasonable tensor to scalar ratio and reasonable spectral tilt. But as I said in this summary slide, that the choice of potential is pretty generic. You can choose to use any potential, and you can. The main idea is that our non-canonical Lagrangian, where the kinetic terms are coupled. That's it.
What?
Yes.
Well, what could be the effect from non-Bunch-Davies initial conditions?
We have not done that actually. You can use different initial condition, but the Bunch-Davies initial condition is the most standard. Definitely there will be changes if you change to non-Bunch-Davies, but there will be changes in the CMB scales as well. So you have to be very careful if you choose non-Bunch-Davies initial condition, because there can be amplification, or there can be suppression in the power in the CMB scales as well. So I do not know anybody has done this non-Bunch-Davies initial condition in the two-field model, or if there is any motivation in order to do that.
Okay, there are no other questions, Dhiraj. Let me applaud on everyone's behalf. Let me also take this opportunity to thank all the three speakers, Yasin, Rajiv and Dhiraj. We are behind schedule, but nevertheless, we will start the next lecture on time at 12 o'clock. Thank you.
Thank you.